The following Zoom session is being recorded and will appear later today on my YouTube channel, Math with Mayo. When you participate in the Zoom meeting, if you do not wish for your picture or your name to be made public, please leave the video off and use an alias name. If you have questions during the meeting but do not wish to speak, email me at vmayo@ybcc.edu and I will respond as soon as I can. So today we're going to start off with, if you have any questions from over the weekend, section 9.4. Then we'll wrap up the chapter with section 9.5. The homework tonight will be 9.5 as well as the chapter review. Tomorrow there are no classes, there'll be no Zoom meetings, no office hours, nada, zip, zilch. It's advising day. Wednesday we will be reviewing for the chapter 9 test, and then Thursday you'll take your chapter 9 test. So there you have it. Do you have any questions from section 9.4?
No, I don't have any.
Alrighty, no surprises there. So let's take a look at section 9.5 and we'll get underway. So 9.5 is about solving radical equations. So equations containing square roots or cube roots or fourth roots, etc., etc. And I'm going to start out with a basic problem that says the square root of the quantity x minus 10 equals 1. All right. Now, when we have an equation with one square root like this, we treat it kind of like an equation with one absolute value. And that is, we want to isolate that completely. In this case, it's already isolated. Just the radical is on one side of the equation and everything else is on the other side of the equation. What we're going to do is we're going to square both sides of the equation. The square root of the quantity x minus 10 squared is x minus 10. So the square gets rid of the square root. On the right side of the equation, in this case, 1 squared is still 1. So we get x minus 10 equals 1. Any questions so far?
Nope.
All right. Then we'll add 10 to both sides of the equation, x equals 11. What's left to do is to check our work. So we'll go back to the original equation and we'll put 11 right there. So that gives us the square root of 11 minus 10 equals 1. The square root of 1 equals 1. The square root of 1 is 1. 1 equals 1. So it checks. So x equals 11 is the solution. Any questions? All right.
No.
We'll go on. Let's say I've got the equation, the square root of 6x plus 1 equals 5. Again, I have one radical expression, one radical term. It's already isolated. It's a square root, so I'll square both sides of the equation. When I do that, I get 6x plus 1 equals 25. Going from there, subtracting 1, 6x equals 24, divide by 6, x equals 4. Let's go ahead and check our solution. 6 times x, 6 times 4 plus 1, 24 plus 1, 25. The square root of 25 is 5, 5 equals 5, and the solution checks. Okay, now life's going to get a little bit more complicated. Let's say we've got the square root of the quantity 2a minus 3 plus 3 as a separate term equals a. So here again, I want to isolate the radical expression or the radical term. So I'll subtract 3 from both sides and I get the square root of the quantity 2a minus 3 equals a minus 3. I'll square both sides of the equation. On the left side of the equation, we get 2a minus 3. On the right side, however, we get a minus 3 times a minus 3, which is a squared, minus 3a plus 9. Don't forget, when you FOIL a binomial, there's those middle terms. Simplifying both sides of the equation, we get 2a minus 3 equals a squared minus 6a plus 9. This is a second degree equation. So I'm going to put everything on one side of the equation set equal to 0 on the other side of the equation. I want my leading term to be positive, so I'm going to leave the a squared where it is, and I'm going to subtract 2a from both sides and add 3 to both sides. This gives me 0 equals a squared minus 8a plus 12. Okay, now we have a second degree equation in standard form. Factoring it, we're going to get, let's see, minus 6 and a minus 2. Okay.
Yes.
That means good. A equals 6, A equals 2. And we'll go back and we'll check our work and see if those solutions do in fact work. Okay, let's take A equals 6. And let's see if I'm going to have enough room to put this here. I would have the square root of 2 times 6 minus 3 plus 3 equals 6. Keep in mind, this 3 right here wasn't there at the beginning. So that gives me the square root of 12 minus 3. Oops, I wrote plus and didn't put it plus 3. And then plus 3 equals 6. The square root of 9 plus 3 equals 6. 3 plus 3 equals 6. 6 equals 6. So that first solution works. A equals 6. Okay. Now let's take a equals 2 and try that one. The square root of 2 times 2 minus 3 plus 3 equals 2. The square root of 4 minus 3 plus 3 equals 2. The square root of 1 plus 3 equals 2. The square root of 1 is 1. 1 plus 3 equals 2. 4 equals 2. Yeah. Okay, so here we have two potential solutions. The first one, a equals 6, works. The second one, a equals 2, does not work. Now, when you square both sides of an equation, or when you raise both sides of an equation to a power, squared, cubed, fourth, whatever, sometimes you create what are called extraneous solutions. That's kind of a strange word, I know. Those are solutions that we arrive at, but yet when we check them, they don't work. So for this problem, the two potential solutions were a equals 6 and a equals 2. A equals 6 is a correct solution. A equals 2 is not a correct solution. It is called an extraneous solution and does not work. Okay. Any questions there?
No, not so far.
All righty. Let's see here. Let's take a look at this problem. The square root of 3x plus 5 equals 2. Okay. So once again, I want to isolate the radical term. So I'll subtract 5 from both sides. The square root of 3x equals -3. Okay. Now, squaring both sides, I get 3x equals 9. Dividing by 3, I get x equals 3. However, when I put x equals 3 back into the equation, I get the square root of 3 times 3 plus 5 equals 2. The square root of 9 plus 5 equals 2. The square root of 9 is 3. 3 plus 5 equals 2. 8 equals 2. No, it doesn't. So no solution. All right with that?
Yes.
Okay, sorry. Now I want to point something out. Right back here when we had this, at that point, it would be obvious, if you thought about it, that there's no solution, because when you take an even root, you can't get a negative number. However, sometimes in WebAssign, it will ask you to go on and get the potential solution and then say that it doesn't work. Other times it'll just ask you to say no solution. So I just wanted to go through and show you that if you just carried on, got your answer, and then checked it, it wouldn't work. But you could look at this and say, oh, it's not going to work. But again, WebAssign asks different kinds of questions depending. So just be aware of that. All right, now, what if we have the cube root of 12m plus 4 equals 4? Once again, we've got the radical term isolated, but now we don't have a square root, we have a cube root. Do you know anything about the story about Noah's Ark?
Yes.
Do you know what dimensions they
I
used?
have some.
What?
Wasn't it like 40 by 40 or something?
But what units were they?
I don't know.
They were cubits.
I don't know that.
Okay, a cubit is the distance from your elbow to your fingertips. Why do I say that? Because that's what we're going to do here on both sides of the equation. We're going to cube it. Okay, sorry, bad joke. Okay, so because it's a cube root, we cube both sides. On the left side of the equation, we get 12m plus 4. On the right side of the equation, we get 4 cubed, which is 64. All right, going on and solving for m, we'll subtract 4 from both sides, divide both sides by 12, and we get m equals 5. So now let's check our work. We've got the cube root of 12 times 5 plus 4 equals 4. The cube root of 60 plus 4 equals 4. The cube root of 64 equals 4. And finally, 4 equals 4. It checks. The solution checks. It's correct. All righty. Let's say we've got something like this. The quantity 2b plus 29 to the 1/3 power equals 3. Now, something raised to the 1/3 power, it's the same thing as taking the cube root of it. So again, we want to isolate that term. It is isolated. We will cube both sides and get 2b plus 29 equals 3 cubed, which is 27. Solving for b, we'll subtract 29 from both sides. We get b equals -2. Divide both sides by 2, and we get b equals 1. Checking our work, we get 2 times -1 plus 29 all to the 1/3 power equals 3, which gives us -2 plus 29 to the 1/3 power equals 3. 27 to the 1/3 power equals 3. 27 to the 1/3 power, cube root of 27, 3 equals 3, checks. So the solution checks. All right, let's see here. Here we have a situation where we have 2 radicals, and in that case, we want them separate from each other, and it turns out in this problem, they already are. So we've got the square root of m plus 4 equals the square root of 2m minus 5. Squaring both sides of the equation, we get m plus 4 on the left, 2m minus 5 on the right. Now, solving for m, I'm going to solve for m on the right. So I'll subtract m from both sides. 4 equals 1m minus 5. Add 5 to both sides. 9 equals m. Let's check our work. The square root of 9 plus 4 equals the square root of 2 times 9 minus 5. My voice is cracking up this morning. Which is the square root of 13 equals the square root of 18 minus 5. Square root of 13 equals the square root of 13. Now, off the top of my head, I don't know the square root of 13, but I do know that the square root of 13 equals the square root of 13. So that checks, and our solution, m equals 9, is correct. So if we have 1 radical in an equation, isolate it. If we have 2, separate them, 1 on each side of the equation. Okay. Let's see here. Let's take a look at solving some formulas for a specific variable. this says D equals 1.4 times the square root of H, and we are to solve for H. Now, the term with the radical is isolated. 1.4 is not a separate term from the square root of H. It's being multiplied, so it's all the same term. But we have a choice here. We can leave the 1.4 where it is and square both sides, or we could divide both sides by 1.4 and then square both sides. Either way, we'll end up with the same result. Is there a particular way you'd like me to do it?
You can divide first.
All right.
By 1.
So we'll divide by 1.4 and we get D over 1.4 equals the square root of H. So now we will square both sides. On the left side, I have D squared over 1.96. On the right side, I have H. So we've solved for H. H equals D squared divided by 1.96. All right with that?
Yes.
I'm going to go back and I'm going to do it the other way just to show you how that would work out. So if we have D equals 1.4 square roots of H, and I squared both sides, I'd have D squared equals 1.4 squared, the square root of H squared. D squared would be 1.96H. Divide both sides by 1.96. And again, H equals D squared over 1.96. So it doesn't matter. The thing you got to be careful of, though, is notice here, I'm squaring this and that, okay? So it's not just 1.4H. I've got 1.4 the quantity squared, the square root of H, the quantity squared. Okay. Let's see here. Let's take a look at this one. D equals the cube root of the quantity 12V over pi, and we are to solve for V. V is locked up inside of a cube root. The cube root is isolated, so I'm going to cube both sides of the equation. On the left side, I get D cubed. On the right side, I get 12V divided by pi. Solving for B, I'll multiply both sides by pi, which will give me pi D cubed equals 12V. Then I'll divide both sides by 12, and I get V equals pi D cubed over 12. So once again, we've solved for the variable, in this case, V. All right. Let's take a look at this one. If you need more time to write anything down, please let me know. R equals the cube root of the quantity A minus P, or excuse me, A divided by P, and then minus 1 is outside of the radical, and we're to solve for P. So again, we want to isolate the radical. So my first move is going to be to add 1 to both sides. So I'll get R plus 1 equals the cube root of the quantity A divided by P. The next step, I will cube both sides. I get R plus 1, the quantity cubed, equals A divided by P. Now we have to be careful here. We want to get P by itself, but P is in the denominator. So if I just get rid of the A on top, I won't have P. I'll have 1 over P. I need for P to be in the numerator. So my next step, I'm going to multiply both sides by P, which gives me that. Then I'm going to come back and divide both sides by the quantity R plus 1 cubed. So P equals A over R plus 1, the quantity cubed. You could multiply R plus 1, the quantity cubed out, but you don't need to. Okay. How about, let's see here. this one. 3 cube roots of x equal the cube root of 3, excuse me, the square root of, I was doing cube roots before, sorry, square roots. 3 times the square root of x equals the square root of 3x plus 54. So I have 2 radicals. They are isolated. I'm going to square both sides. Now on the left side, I'm not going to get 3x. Remember, I'm going to get 3 squared, the square root of x squared. So I'm going to get 9x. Okay with that?
Yes.
And on the right side, 3x plus 54. So now I'm going to solve for x on the left. I'll subtract 3x from both sides. 6x equals 54. Divide by 6. X equals 9. 3 square roots of 9 equal the square root of 3 times 9 plus 54. Let's see. 3 times the square root of 9, 3 times 3, which is 9. And on the right side, 27 plus 54, which is 81. The square root of 81 is 9. 9 equals 9. And the solution x equals 9 is correct. Okay. How about this one? We have the quantity m to the 4th power plus m squared minus 25 all to the 1/4 power equals m. So I've got one radical or term with a fraction exponent, because the 1/4 power would be like the 4th root. So now I'm going to raise each side to the 4th power. On the left, I get m to the 4th plus m squared minus 25. On the right, I get m to the 4th power. Okay. Now, this is a 4th degree equation. So our strategy would be to get everything on one side of the equation set equal to 0 on the other. I'm going to put it all on the left. But when I subtract m to the 4th power, now it's no longer a 4th degree equation. It's a 2nd degree equation. Same strategy though. In fact, now what I've got is the difference of 2 squares. So m plus 5 times m minus 5 equals 0. So if m plus 5 equals 0, we subtract 5 and we get m equals -5. M minus 5 equals 0. We add 5 and we get m equals +5. So we've got 2 potential solutions. Let's check our work. Let's take the -5 first. Okay, so we've got -5 to the 4th power plus -5 squared minus 25 all to the 1/4 power equals -5. Okay, which is, let's see, negative times negative times negative times negative would be positive, and -5 to the 4th power is 625, plus -5 times -5 would be 25, minus 25 is all that to the 1/4 power. Well, 625 plus 25 minus 25 would be 625 to the 1/4 power, which is 5. 5 does not equal 5, so that's an extraneous solution. Okay, does not work. Let's go back and let's plug in the +5. We would get 5 to the 4th plus 5 squared minus 25 all to the 1/4 power equals 5. 625, that cancels to the 1/4 equals 5. 5 equals 5, and that one checks. You may have noticed that when we take odd roots, it seems like the solutions work. When we take even roots and we square both sides or raise both sides to the 4th power, that's when we run into some problems. Yeah, just something to think about. Okay, now This says, okay, I want to do this one. It says, let f of x equal the fourth root of the quantity x plus 8 minus the fourth root of the quantity 2x. Okay, then it says find all values of x for which f of x equals 0. And I think the reason the author puts these problems in here is just kind of to reintroduce function notation. What we're basically going to do is a substitution. If f of x equals 0, then that's going to go right here. So our equation is going to become 0 equals the fourth root of the quantity x plus 8 minus the fourth root of 2x. Remember, I said if we have one radical expression, we want to isolate it. If we have two radical expressions, we want to separate them. So I'm going to add the fourth root of 2x, to both sides of the equation. So now what I have the fourth root of 2x equals the fourth root of x plus 8. Okay. I will raise both sides to the fourth power, and I get 2x equals x plus 8. Subtract x, x equals 8. Let's check our work. If x equals 8, we would have, so plugging it right in there, we would have 0 equals the fourth root of 8 plus 8 minus the fourth root of 2 times 8. Okay? 0 equals the fourth root of 16 minus the fourth root of 16. Now, the fourth root of 16 turns out to be 2. So I get 0 equals 0, and this one works. But even without doing that, wouldn't you agree that the fourth root of 16 would equal the fourth root of 16? So the fourth root of 16 minus the fourth root of 16, you'd get 0 equals 0, either way. Okay. Let's see here. How about let's see, how about this one? X to the 1/2 power plus 6 equals 8. So even though x to the 1/2 power isn't written in radical notation, it's still going to give us what, like a square root. So I'm going to isolate this term. I'll subtract 6 from both sides. X to the 1/2 power equals 2. Square both sides, x equals 4. Let's check our work. If x is 4, we get 4 to the 1/2 power plus 6 equals 8. 4 to the 1/2 power is 2. 2 plus 6 equals 8. 8 equals 8, and it checks. All right. Let's see. I think that's enough for today. So to wrap up here, we'll do section 9.5 in the chapter review tonight. Tomorrow, no class. Wednesday, we'll come in and we'll review for the chapter 9 test, which we'll take on Thursday. So I'm going to stop the recording.